My name's Deborah Harford. I run the Adaptation to Climate Change team at SFU. And the next panel will look at key ecological research and considerations for Columbia River Basin health across past, present, and future. And the issues that our speakers are going to explore have major significance for the treaty negotiations, given the increasing overall prioritization of ecological health. So you've met our first speaker already, John O'Riordan, but I want to give everybody a little introduction. I'm not sure that John did himself justice. So John is a former Deputy Minister for the Ministry of Sustainable Resource Management. He's a senior policy analyst with your hosts, Polis Center for Ecological Governance here at UVic, and also with my organization, the Adaptation to Climate Change team at Simon Fraser University. And John's going to speak about restorative opportunities in the Columbia Basin. Thanks, John.
So good morning again, everybody. As Deb mentioned, I work both for ACT, which is the Adaptation to Climate Change team centered at Simon Fraser University in Vancouver, and also working with Oliver Brandeis here at Polis. But ACT was provided some resources to do some work with the BC government on looking at restorative economics in the Columbia, and I want to talk a little bit about that. So these are the main points that I wanted to cover in my 10 minutes. First, that ecosystem function is now embedded as one of the key values to be included in the renegotiated Columbia Treaty. There's now a question of whether or not and how monetary value should be applied to ecosystem function. That's controversial, but I'll speak to that as the main point in my presentation. I'm going to introduce the work that Marcus Norbitz is going to be talking to about how changing climate is going to affect values over time. And I'm going to recommend at the end of the session that we should be looking at scenarios that link ecosystem function, flood control, and power in a renegotiated Columbia Treaty. So the issue really is not only do we need restored value, but how do we value that? So the currency of the treaty at this point in time is in US dollars. So as you've heard from Bob Cousins, that the original flood control agreement, somewhere around $64 million was paid to the BC government to pay for 60 years of flood control. And the Canadian entitlement is also in dollars, and it now varies between $100 and $200 million a year in terms of power benefits. So the question is, should ecosystem function also be applied to in dollars so that it can compete with these other two factors in a renegotiated treaty? And so to do that, a number of pieces of study have been done over the last 3 or 4 years. The first was by ACT itself, which undertook an analysis of ecosystem function and economics about 3 years ago, and I was part of that study. The second is a study was commissioned by the US tribes in the Columbia to a group called Earth Economics that looked at the value of natural capital in the Columbia. That was completed a year ago. And there was also some work done by a Berkeley team that met a year ago in San Francisco and University of Berkeley and developed a set of principles around ecosystem restoration. And finally, my friend Mike Miles has been heavily involved in river restoration, which includes the Columbia, although not putting yet values on that. So there are several values associated with ecosystem function, some of them monetary and some of them non-monetary. One is called provisioning goods and services, so water, hydropower, soils, irrigated agriculture, and forests are all components of the natural ecosystem that convey value in terms of resource use and development. Also, the regulating services, so water provides controls, natural controls. So wetlands provide a series of controls on flood development, erosion control, improved water quality, and more recently, the whole ability to store carbon. So restored watersheds have an increased capability to restore carbon, and in a carbon constrained world, ecosystems that can store more carbon have become more valuable, as we are unable to control the amount of carbon we emit into the atmosphere. And finally, there's a whole lot of spiritual and cultural values, a lot of which are associated with First Nations Indigenous rights that are associated with ecosystem function. So these are all important values and need to be included in the renegotiated Columbia Treaty. So what ACT did 3 years ago was to look at the potential value of some of these sets of ecosystem functions across the entire basin, just to get a sense of the size of the value. And we concluded that and there are economic techniques for doing this, which I won't go to in detail in the 10 minutes I have, but they are acceptable by economic scientists and economic theoreticians in the development of ecosystem economics. But we found out that the value of the basin, the ecosystems across the Columbia Basin are in the low billions a year, so somewhere between $1 and $5 billion a year associated with provisioning and regulating services. And that if we, right now, because they're not valued formally in any of the analysis being done by the current resource development proposals and scenarios, they're considered to have a value of 0. But it's not 0. There's a real value associated with these ecosystem functions. It may not be formally in the billions, but it needs to be included in the analysis. So we tried to find ways to make this more relevant. So some of the ways in which we can determine value in fisheries, for example, is what one of what's called existence values, where people are asked what they would be willing to pay in order to retain the right to have fish in the Columbia. And there are a number of studies that were done which give proxy values of what people said it was worth their time willing, what they'd be willing to pay in order to keep fish in the Columbia. The second are the actual commercial values of the fisheries itself. So the landed value of fish and the values associated with sport fishing. And thirdly, there's the amount of money that's actually been spent on salmon restoration. So Bob mentioned that in the Columbia, under the Species at Risk Act, I think it was 1973 when that was brought into the Columbia. So salmon is designated as a species at risk. The entities in the Columbia have spent over $13 billion trying to restore the salmon population into the lower Columbia. So that at least is some indication of the value that people are willing to invest to not to restore the full salmon population, but to maintain an existing salmon population. There's also a market value associated with irrigated water that is growing in its amount on an annual basis as the system dries. And recreation, there's many ways to value the amount of money people spend while recreating, and that represents a value associated with the use of the river for recreation and fishing. So, to cut a long story short, what we try to do is make the billions of dollars that potentially are on the Columbia Basin in terms of ecosystem function more relevant to the questions that we were asking. So we assumed that because of the existence of the three treaty dams in Canada, their coordinated storage and release would offset by 5% what would otherwise be the impacts of a changing climate on the Columbia downstream of the border. So in terms of fisheries, mainly, and on irrigated agriculture. So we came to the conclusion that if we avoid, on average, 5% loss to fisheries and provide 5% more water for irrigated agriculture and provide sufficient water in the reservoirs for sport fishing, that the amount of the value of that would be equivalent to about $200 million a year. Now, it's interesting that the Canadian entitlement is roughly $200 million a year, and that's what the Americans pay for incremental power to Canada. But actually, if you look at what's happening today, a fair bit of the water that's released from Canada isn't actually used to generate more electricity. It's actually used to maintain flows in the Columbia for salmon, and in some cases for providing additional irrigation water. So the Americans may bellyache that they're paying more than their share of incremental power, but in fact, they're also paying, as part of that money, to maintain flows in the Columbia for ecosystem purposes. So we're saying that as a very minimum, the value of ecosystem services in the Columbia is equivalent to the current Canadian entitlement, and that in any future negotiation, both the entitlement in power terms, but also the entitlement in delivered ecosystem services for fish, irrigated agriculture, and flood control should also be included in the calculus. So we looked at 3 different ways of measuring that to help the negotiators come up with some approach. One is to look at proxy values of hydropower. So the question here was, if you change the shape of the water flow across the border so that you increase the value in Canada for ecosystem value, for example, stabilizing the lower Arrow Lakes, and I think Greg is going to talk to that in his presentation. That brings ecosystem values to Canada, but reduces the potential amount of water going down to the States for the Canadian entitlement. And so the proxy value is that if you reduce the hydropower in the States, but you gain beneficial ecosystem services in a more better regulated lower Arrow Lakes, then you can calculate whether that's in the realm. In other words, if it costs Canada to pay $50 million because of reduced power benefits to states, is that reasonable? $50 million in increased benefits around the Arrow Lakes because of a more stabilized lake level in the Arrow Lake. So that's one way of dealing with the ecosystem values. The second is actually to build some scenarios, different ways of regulating the Columbia under a renewed or revised treaty, and then use proxy values for fisheries, irrigation, carbon storage, and recreation, and actually measure what these scenarios deliver in different forms. So some with high values of ecosystem management and some with low values of ecosystem management, and compare these with the traditional values of flood control and power and see how they line up. So that's the second model. And the third model is to negotiate as best guesses over 5 to 10 year increments, and then use experience gained over the 10 years to renegotiate that bundle of goods and services for the next 10 years. So in other words, you actually guesstimate what you think would be the optimum balance between flood control and power and maintaining and improving ecosystem function. Have that as an agreement, run it for 10 years, then reassess what reality happened over that 10 years, and then renegotiate the next 10 years based on more experience. So that's the recommendation that we made. The other major study that was commissioned by, and Jim Heffman, I think that's correct, that you folks in the tribes did commission Earth Economics. It's a large economics firm centered in Tacoma to do a major study on ecosystem values in the Columbia Basin. I believe that's entire Columbia Basin, US and Canadian. And they came up with not similar values to the work that we did in ACT, but much more rigorously developed. It's a very major report. And they used the concept of proxy values. So they developed a scenario, or 2 scenarios. One, business as usual, how the Columbia is currently regulated for flood control and power. And one where there would be a deliberate change in the regulation of the Columbia to increase ecosystem value retention, both in Canada and in the States, and forego around $70 million worth of hydropower. So they calculated that based on their economic assessment that you could lose annually about $70 million in hydropower, but you would gain something in the order of $1.5 billion in increased ecosystem values on both sides of the border. So they strongly felt that ecosystem services has a major role to play in the renegotiated Columbia Treaty. They also recommended a whole series of research projects that would more quickly focus what these values were and sharpen the differences in developing scenarios to make them work. And the only other report I'm going to speak to, because I want to leave time for other panelists, is work that was done by the Canadian side of the Columbia a year ago, where they held a workshop in Nelson to look at ecosystem function in Canada and develop a report that did two things. One is what would be the key objectives for ecosystem management in the Columbia portion of the basin, and what are the performance measures that indicate that we're successful in achieving that. And they looked at a number of ecosystems, and Greg Utsik, who's one of our panelists, was part of that discussion, and he may be speaking to what came out of it. But they looked at terrestrial habitats, on the effect on terrestrial wildlife mainly, aquatic systems, riparian wetland ecosystems, indigenous values associated with ecosystems, habitats, tributaries, and carbon sequestration. So a lot of the work they found is that it is possible to change the way in which particularly the Arrow Reservoir is managed compared to what has been happening in the last 60 years, to stabilize the regime so that it doesn't fluctuate as much. And I heard the minister this morning concerned about large areas that are exposed in the late summer, dust flying around in the upper part of the Lower Arrow Reservoir. And the idea is to narrow that range significantly when you have a new flood control agreement, and bring back some of these values on fisheries, terrestrial aquatic ecosystems and wetlands, and include some repatriation of agricultural and forestry values on around the reservoir, which would greatly reduce the original impact of the reservoir. So, Greg, I'm not sure whether you're speaking specifically to the Mid-Arrow, but I'm going to let you carry on with that discussion. So, my conclusions are as follows from the work we did with ACT, and I want to bring these to your attention today. One is that ecosystem function is important, and it actually has to be restored. It's not a question of maintaining what we have. A resilient Columbia is only one which has more improved ecosystem function than we have today. And given the work that Marcus Norvis will be talking about in the changing climate going forward, the more robust and resilient the ecosystems in the Columbia are, the better they are buffered against the kind of changes that are coming in hydrology and climate into the Columbia Basin over the next 50 years. The third point is that while putting economic value to ecosystem function is a bit messy, it's not totally imprecise. And my argument is that in a renegotiated Columbia, when ecosystem function is jostling with commercial values associated with flood control and power, it is important to place some value in dollar terms on key ecosystem functions so it can play a more prominent role in bundling negotiated packages of flood control, hydropower, and ecosystem services in a renegotiated Columbia. So we're not there yet, and my plea is that by the end of today, through the work being presented by the next two panels of speakers, we start to map out a thoughtful set of science work that needs to be done to combine economics and natural system biology, geology, and hydrology, so that we can provide a more informed basis for negotiating these bundles of values. So thank you very much for your attention.
Thank you, John. I'm going to, if there is a quick clarification, anybody has a quick question, we would like people to come up to mics, even if just for succinct question at this point, where there will be 10 minutes for discussion at the end. Okay, so not seeing any questions right now. So I'm going to introduce our next panelist, Marcus Schnorbus. Marcus is a hydrologist with the Pacific Climate Impacts Consortium here in Victoria. And Marcus and his team have been working to produce hydrologic projections for the Peace, Fraser, and Columbia basins for use in the development of climate change adaptation plans for water resources management. So great to have you, Marcus.
Thank you. Thank you all for coming. Next 20 minutes, as discussed, I'm going to take you through a little bit of a broad overview. It'll be general. 20 minutes doesn't allow a lot of time for detail, but we will discuss how we see climate change potentially affecting the hydrology of the Columbia River Basin, and in particular, what's perhaps quite relevant is how that may affect streamflow regimes at various different parts of the Columbia River watershed. Now, assuming I get this right. So just a brief outline, we'll give a little bit of background. I'll spend most of the time talking about what the actual effects of climate change, what we foresee them to be, and then we'll conclude with just a brief highlight of some of the major talking points. You've seen this, of course. This is just a slide of the Columbia River Basin. I won't spend a lot of time. You've got lots of background, but suffice to say, the entire Columbia River Basin, the tidewater, is a significantly or substantially large piece of real estate, 630,000 square kilometers plus change. The four treaty dams, Mica Dam and Keenly Side Dam, are on the Columbia main stem in the upper headwaters of the Columbia, and Libby and Duncan are on the Kootenay. And if we take sort of the drainage area sort of defined by those two tributaries, we end up with what I would call the upper Columbia here. It's an area of 86,000 square kilometers. It's only about 13% of the entire Columbia, but as you can see, it can be a rather significant hydrological component of the basin itself, despite its relatively small size. Also note that most of that region is obviously in Canadian territory. Some of it is in the US, and note that that does not include other parts of the Columbia that are in Canada, specifically the Okanagan, the Kettle, and the Granby. Effects of climate change. Let's begin. So the first thing we're going to look at is temperature. I should back up a bit and say there's a slide that wasn't in there. The IPCC, Intergovernmental Panel on Climate Change, concluded in their fifth assessment report published in 2013 that it is extremely likely that observed trends in temperature change over the globe are attributable to anthropogenic emissions of climate change. It is anticipated that as we continue with greenhouse gas emissions into the atmosphere, those trends will continue. They will result in local, regional, and global changes in temperature and precipitation, and those changes will have what we will see consequent effects on the hydrology of this region. The first thing we're going to look at is temperature. And what we're going to do is show results of essentially a modeling exercise. And what this looks at is two scenarios. Because we can't predict or we can't specify what future emissions are going to look like, the global climate community comes up with what they call emission scenarios, called representative concentration pathways, looking at a range of possible futures. The two scenarios that we are looking at are what we call RCP 8.5 and 4.5. I won't get into the details of what the numbers means, but essentially RCP 8.5 is what we would consider a worst case scenario, business as usual, resulting in greenhouse gas concentrations at the end of the century that would be 3 times higher than pre-industrial levels. And that's really a world without any kind of mitigation. RCP 4.5 is a scenario that presumes that there will be some type of mitigation, that we would stabilize emissions by mid-century and concentrations would stabilize by end century. Pick your poison. It's hard to say which one is more likely, but we'll look at both of them. And what we're looking at is seasonal temperature, winter, spring, summer, fall, over the entire Columbia River Basin, looking at it from the historical period, 1950, all the way to 2100. And what you can see in all 4 seasons is a rather consistent picture of we expect temperatures to increase as greenhouse gas emissions continue to increase. A very clear signal. Obviously, the 8.5 scenario would result in higher temperatures than the 4.5 scenario. As clear as the temperature signal might be, the precipitation signal is perhaps not as clear. Same idea, looking at 2 different emission scenarios, looking at potential precipitation changes in winter, spring, summer, and fall. And what we see is a lot of what we call interannual variability. There's a lot of differences. The solid red line is a median of 5 different global climate models. The band shows the range between various different global climate models. So there's a tremendous amount of uncertainty, and there's a bit more ambiguity about how precipitation might change in the future by what we see happening with temperature. Because we're dealing often with noisy variables, what we sometimes do in order to make simpler comparisons is we divide the record into climatological periods, 30-year periods. We establish a reference period that is essentially the last 30 years of the 20th century, 1971 to 2000, and we compare that to two future periods, a mid-century period centered on the 2050s and an end-century period centered on the 2080s. We take averages during those periods and then compare them to each other and try to filter out some of this noise. And what we see with precipitation is what emerges as perhaps a bit clearer picture. Looking at mid-century and end-century, we see winters getting wetter and summers getting drier, or that's our expectation. As we get further into the future, of course, that trend just gets larger. So wetter winters, drier summers. What's not shown in this graph is 3 of the 4 seasons, winter, spring, and fall, are expected to get wetter, and summers, which are already dry in the region, are of course projected to see increased or decreased precipitation. This obviously will have implications on the seasonality, definitely, of hydrology. The next slide looks at snow accumulation. In much of the basin being dominated by interior type climates, the seasonality of snow in the Columbia, in most of the Columbia, with the exception perhaps of the coastal margin, is dominated by the processes of snow accumulation and snow melt. So you can imagine that changes in temperature and changes in precipitation could potentially have very profound effects on how snow accumulates, how much snow accumulates, and the rate at which it melts and when it melts. We start with just to look at a baseline snapshot of what typical snow accumulation would look like at the end of the 20th century. The scale goes from 0, which is white, to as high as 2,000 millimeters, which is the dark purple colors. And some of the features that immediately jump out at you, of course, is the magnitude of snow accumulation is obviously very closely correlated with elevation. So the areas of highest snow accumulation tend to be the Cascade Crest, tend to be the high points in the Rockies in the United States. But what really strikes you and what really jumps out is how much snow actually accumulates in the upper Columbia compared to the rest of the basin. So a substantial amount of natural snow storage is actually occurring up here in the upper Columbia. Obviously, as we look to a future with warming temperatures and changes in precipitation patterns, we expect that the pattern of snow accumulation will change in the future as well. So this is looking at worst case scenario, RCP 8.5. This changes in what we call peak snow water equivalent, but we use essentially the date of April 1st as a proxy. And look at how peak snow water equivalent is expected to change in the middle of the coming century and the end of the coming century. And the scale essentially goes from 0, no change, to complete loss of snow cover, minus 100%. What should immediately jump out at you is there's no pluses here. We anticipate that snow accumulation is decreasing everywhere. There's nowhere in the basin, despite wetter winters, there's nowhere in the basin where we anticipate increasing snow accumulation. However, obviously the most vulnerable snowpacks are those that are at lowest elevation. The least vulnerable are those that are at higher elevation. And again, and obviously the trend just increases from mid-century to end-century, where a lot or most of low elevation snow by the 1st of April we anticipate will have disappeared. Again, what's striking is although we anticipate we will lose snow in the upper Columbia, that is sort of the last bastion of snow in the basin by the end of the century. So there will be loss of snow, but not nearly as severe as some other parts of the Columbia. This, of course, has consequences on what we expect stream flow to look like in the future. To sort of take a look at that, we're going to look at 3 sites along the main stem of the Columbia. So the 3 sites I chose are the Columbia River at Nicholson, which is essentially the farthest downstream section of the upper Columbia that is unregulated. So this is just upstream of Kinbasket Lake. We'll look at a site that I call the Columbia River at Murphy Creek, which is essentially the runoff from what I call the upper Columbia. And then we'll take it all the way down to Bonneville Dam, which is essentially the last structure or regulation structure on the main stem of the Columbia just before tidewater. So this is a rather busy graph, 3 slides. Columbia River at Nicholson is the hydrograph at the top is the Columbia River at Nicholson, 6,600 square kilometers. The hydrograph in the middle, Columbia River at Murphy Creek, or the Upper Columbia, and this is the entire Columbia. We're looking at 3 different periods. The colors, gray represents the baseline period. Blue is what we expect or what we're projecting for mid-century. Salmon, or red, is what we're projecting for the end of the century. This is for RCP 8.5, again, I guess the worst case scenario. And this is monthly average stream flow. The first thing that sort of jumps out is that you look at the gray line, and what's immediately apparent is this is the classic signature of what is essentially a snowmelt-dominated system. You have very low flows in the wintertime, when historically most precipitation is stored as snow. You have a large springtime freshet, melt essentially starts in April but begins in earnest in April, and you have a peak, depending on where you are, in the period of June or July. And then you have a rapid recession, and then we have low flows during the summer, and then back into the winter, the fall and winter. So this is what we would call essentially a nival regime. Because of the anticipated changes in precipitation and snow, one of the things you're seeing is warmer temperatures mean more rainfall and less snow in the wintertime. So we're seeing an increase in wintertime temperatures. In many cases, we're seeing a dramatic shift in the seasonality of the freshet. It's starting to happen earlier in the year. The occurrence of the month of peak discharge is expected to happen earlier in the year. And that trend or those changes just become more pronounced as we go from mid-century to end century. And also a significant feature or signal of these changes in stream flow is a rather large decrease in summertime discharges that are anticipated in all 3 locations. What's interesting is I'm not sure how significant it is. It depends on how the system is regulated. But as we move from the headwaters down to the outlet, we come to a situation where in the future, the freshet peak is expected to be larger than it is historically. But as we get to the outlet of the basin, we see that it may actually be smaller. So there is some difference spatially in how those systems may respond as we move from headwaters to the outlet. The final slide is to try to relate how changes in the Upper Columbia may relate to changes in the Lower Columbia. There has been some discussion or allusion to the fact that, and I've said so myself, that the Upper Columbia can represent a disproportionate amount of runoff for the entire system. So what this graph shows is, again, looking at RCP 8.5, and looking from 1950 to 2100 and graphing every year, taking the ratio of runoff from the Upper Columbia to the runoff in the entire system and looking at those ratios. And what's probably most significant is in the summertime, in the spring and the summer often representing those peak freshet months. Historically, about 30% of that total discharge comes from the Upper Columbia. Remember, that area is only 13% of the total basin. So in the summertime, so during sort of peak freshet and summer flows, 30% historically, potentially increasing to 35, although that's likely not a significant change. 30 to 35% of total runoff in the Columbia will come from essentially the Upper Columbia. Not as significant in the fall and the winter, but again, the winter and spring. Summer, the most significant. In fall as well, the Upper Columbia can be a significant contributor to total runoff. Although it doesn't appear that climate change will see those ratios change really all that markedly. And we'll finally conclude. One of the major points, obviously, we see a very robust signal of increased air temperature. Projections for precipitation are present a bit of a weaker signal, a little more ambiguity, but if we reduce some of the noise, it does suggest that we can expect increased precipitation throughout most of the year, with the exception of summer. Obviously, with changes in temperature in particular, we're expecting to see a decrease in snow throughout the basin, but perhaps less so in the Upper Columbia. All of these then result in a change in the seasonality of runoff and stream flow. We would expect more runoff in the wintertime. We would expect an earlier onset of the spring freshet, and also we would expect decreased summer discharge. And of course, well, what seems to be happening is the variation of what happens to the magnitude of spring fresh at peak. It tends to be varies with location. I'm off the hook.
Yeah, we'll just, thanks, Marcus. Can I call for any clarifying questions? Everybody's very satisfied with that. Great. I think we're on track for RCP 8.5, not the lower one. Hopefully that may change. So just a comment. So just introducing our next speaker. So Dr. Kim Hyatt is a research scientist at Fisheries and Oceans Canada's Pacific Biological Station. Kim heads the Salmon and Regional Ecosystems Program, with research interests focused on the status of salmon populations in Canada's Pacific region, climate effects on salmon in freshwater and marine ecosystems, and development of tools to improve fisheries management. I think he's going to speak to all three of those. Thanks, Kim.
Okay, that's not the right PowerPoint.
Kim's speaking again later, so the one he's supposed to be doing now.
There's one on the desktop. That's the one. Okay, I'm going to talk about overcoming challenges to sustaining and restoring wild origin salmon and associated fisheries in Canada in the Columbia Basin. And these are lessons that we've learned from Okanagan salmon restoration over the last 2 decades. First, some Columbia River salmon restoration context. Between the 1800s and the early 1900s, the Columbia River salmon complex represents a classic case of first fishing up and then fishing down on the great species complexes that have supported commercial fisheries there. In 1942, the construction of Grand Coulee Dam eliminated salmon access to the upper Columbia and clearly contributed to the accelerated decline in the aggregate salmon resource that was returning there. In 1991, Snake River sockeye were listed as endangered under the Endangered Species Act in the U.S., and between, in the more recent decades, another 15 populations of salmon were listed under that same act as threatened. With this kind of dire context for the progression of salmon production in the Columbia, I'm going to use this talk to touch on several key elements of restoration and planning and implementation that we've undertaken in the Okanagan over the last 2 decades. The elements really include identification of a vision and a common set of objectives, to look at the legislative and statutory framework and the policy framework that influences implementation of that kind of vision, the establishment of collaborative governance arrangements, on through to assessing the status of watersheds that produce salmon and of the salmon themselves, and finally on to kind of implementation once you've found sufficient funding to suggest that you can implement. So first, what was the vision and where did it come from? The Okanagan Nation Alliance wished to halt and then reverse the declines of Okanagan salmon. Okanagan salmon are the last salmon of Canadian origin that comes through the Columbia River, Grand Coulee having cut off all other production that originally came from Canada. Between 1995 and 2004, low average returns of salmon to the Columbia and to the Okanagan in particular of sockeye salmon, the last major population, created great alarm among the Okanagan Nation Alliance. And in fact, a single year low of less than 1,500 adults came back to the Okanagan in the early 1990s. So if you're going to do restoration, what kind of legislative framework do you have to consider? Well, for a transboundary population of salmon, this is a legislative framework. And it exists on both sides of the border, in Canada and the US. You have parallel systems of agencies. You have 3 international treaties, the Boundary Water Treaty, the Columbia River Treaty, and the Pacific Salmon Treaty. You have numerous policies and, of course, laws that are distinctive to both countries. And the principal challenge here is that there's generally poor integration among all of these. Even among the major treaties between the two countries, the groups that implement these don't talk to each other and don't understand the objectives that actually are contained in those treaties. Collaborative governance within Canada on the Okanagan has been provided by the Canadian Okanagan Basin Technical Working Group, and it was a grassroots formed organization that occurred in the early 90s or mid-90s following the 1996 Visions Workshop that the Okanagan Nation Alliance held. It has formal terms of reference that were signed off by the 3 parties, Department of Fisheries and Oceans, BC FLNRORD, it's hard to, I won't go through the whole acronym, and the Okanagan Nation Alliance. So those are the 3 parties that had the statutory authority or the constitutional interests in restoration of salmon. So what are the status and trends of Okanagan watershed and salmon as indicators of ecosystem function? Well, in the early to mid-1800s, the Okanagan represented a complex of lake and river networks, wetlands, abundant salmon populations, and rich biodiversity. By the mid-1900s, disturbance regimes imposed by contemporary development and human systems increasingly dominated both the terrestrial and especially aquatic ecosystems. Irrigation and flood control, infrastructure now blocked migration at multiple points throughout the Okanagan subbasin, and channelization had reduced the original length of the Okanagan to 50% of its basic length and had eliminated 90% of all wetlands and riparian vegetation. This governance group, Cobb Twig, did an audit in the mid-1990s on the status and trends of Okanagan sockeye and associated salmon and habitat. And what this produced was a report card suggesting the magnitude of the salmon restoration challenges, in that 9 of 12 major classes of threats to salmon were rated as high to severe. These included population growth and urbanization, construction of dams and hydrological regulation, channelization, erosion and sedimentation, wetland destruction, the introduction of pollutants and toxins, something on the order of 29 invasive species, the overarching issue of climate change, and of course, direct exploitation of fish. So within this kind of grim prospect for restoration, the Okanagan group had a deep commitment to science-based planning and analysis, which helped anchor the Okanagan Nation Alliance vision regarding the need for decadal scale planning. And the anchoring really is related to the limits on what we can do in restoring salmon. Salmon, because of their complex life histories, live half of those life histories in the vast expanses of the North Pacific Ocean, where we have virtually no control over them. And they return 2 to 3 years later, having reared in freshwater, to those freshwater systems, and that's the only place that you can gain some restoration impacts. The Cobb Twig group had an integrated restoration plan that included 3 pillars. The first was to rebuild wild origin sockeye salmon, and the time estimated for that was roughly 20 years, 2 decades, which would involve regulating water for fish-friendly flows and increasing adult escapement to take best use of available habitat, both spawning habitat and rearing habitat in river and lake environments that remained. The second pillar was to expand the range of Okanagan sockeye salmon by reintroducing sockeye to Skaha and Okanagan lakes, and also by restoring passage at multiple dam locations along the Okanagan Valley bottom. And then the third pillar was to improve the quantity and quality of off-channel and in-channel habitat for all salmon. And the time scale for entering into that kind of enterprise was something on the order of 4 decades to half a century. So we're being fairly realistic about the time course that it would take to bring about real change. So what's managing hydrology for fish-friendly flows all about? Well, given annual to seasonal risks of either flood or drought in the Okanagan, something demonstrated amply this year, there's a complex system of hydrological control structures to store and release water. Prior to 1997, water management practices exhibited very low compliance with fish-friendly flows that were specified by the Canada-BC Okanagan Basin Agreement. This was something that John O'Riordan had a hand in back in the 60s and 70s. John would be disappointed that many of the features of this actually couldn't be successfully implemented at that time. From 1982 to 97, river discharge exceeded OBA fish-friendly flows in something like 75% of cases for adult migration, spawning, and incubation of salmon together. If regulated flows were in the preferred range, they should really have been within these narrow green bands that you see on this slide. So obviously they departed significantly. So what was the challenge? Well, establishing fish-friendly flows, given the history of competing water management interests, was really the first major challenge. And those interests involve flood protection, the use of water to support agricultural production, the recreational use of water, which you were balancing off against the environmental values of aquatic biota and salmon specifically. Part of the solution to this was to build an advanced fish water management decision support system, where this system is a coupled set of biophysical models of key relationships among fish, habitat, water, and climate that allow water managers to simulate their decisions ahead of time for storage and release of water, either in an operational mode on real time, a retrospective mode to look at historical features, or in a prospective mode going forward. Really consists of 4 biophysical models coupled to a water management rules model, and it's all implemented in software that's internet accessible, which water managers and fisheries managers and others can use in real time to make decisions before they actually have to store or release water, to look at what the impacts will be not only on fish, but also on flood control objectives or irrigation. So what's the result of these 2 particular initiatives? Well, first, the fish water management tool implementation has reduced the density-independent losses of salmon production from flood and scour and drought and desiccation losses in years where it was possible to do that. A year like this year, where you have imminent risk of flood from record snowpacks, means that you have no chance of doing anything on behalf of fish, and water managers are free to do what they can to protect human life and property. But in many other years, they can actually achieve fish-friendly flows, and that reduces the losses attributed to drought and desiccation and flood when you have a given number of spawners. The second initiative was to increase the number of spawners, which would increase the production of juvenile salmon. Over the last decade, this has added about 6 million smolts and associated 180,000 wild origin salmon to wild returns. Remember, I said the low 1-year extreme reach was 1,500 adults in the 1990s. So having more than 180,000 adults come back is a major event. The second challenge was to establish the feasibility of sockeye salmon reintroductions above barrier dams at Skaha Lake and the Okanagan Lake outlets. And the approach to this was to do pilot introductions into Skaha Lake over about a 12-year period on an experimental basis to see if it would work, and it did, and then to find support to build a long-term operational hatchery. That support came from public utility divisions down in the United States who needed fish production credits under their Federal Energy Regulatory Commission licenses. So this hatchery was built without the benefit of any Canadian taxpayer money. And the Skaha hatchery has added roughly 10 to 20,000 adult sockeye per year to returns over the last decade of time. The third challenge is probably the most difficult one, and that's restoring lost habitat and normative ecosystem function. The benefits to date have been relatively modest, only about 5,000 spawners, because what you're dealing with is habitat loss where something on the order of 80 to 90% of the river has been channelized, 50% of its length has been lost, 90% of riparian vegetation and wetlands are gone. And when you want to implement these kind of major restoration projects, here a river meander restoration, you first have to have engineers and hydrologists who don't come cheap, and put detailed plans in place and then implement those plans. The cost of doing this is roughly $1 million per kilometer. And one of the things I haven't mentioned is that there are about 60 kilometers of channelized river in the Okanagan. So one can imagine that you're in for substantial amounts of investment before you're going to see major benefits for the restoration of lost habitat and normative ecosystem function in the Okanagan. However, given these three different strategies that we've used, the cumulative effects of restoration have been nothing short of spectacular. The average returns of roughly 200,000 sockeye between 2008 and 2017 have exceeded even the single-year maximum returns in the 40-year, or is it 50-year period between 1965 and 2005 before this work was started. This has allowed First Nations, tribal, recreational, and commercial fisheries for Okanagan sockeye to be restored not only in Canada, but also in the US. So what are the lessons learned? Well, leadership, vision, and support for a common cause are essential. You need to adhere to key elements of restoration planning, from statutory support to effective governance, careful science-based planning, and rigorous adaptive management. It's important to recognize, assess, and acknowledge limits on manipulating salmon and ecosystem associations shaped by drivers that emerge from natural and human systems where often we're not in control. It's important to critically assess limiting factors and match the space-time scale of restoration actions to the scale at which the factors exert their influence. That is, think globally, but think and act locally. Project and measure restoration outcomes within realistic timeframes. This is 1 to many decades, despite the desire for quick fixes. There is no cheap and cheerful solution here. It's just darn hard work. You should pray for divine intervention and hope for a lot of good luck. We've clearly had some of each. And finally, successful restoration of depleted salmon is sometimes possible and is always an adventure. Thanks very much, and that's the end of the talk about restoring salmon.
Thank you, Kim. Any quick clarifying questions for Kim?
I have one, and I'll just speak up.
Okay. Is that all right?
How did the sockeye get out of Columbia? That's all those dams.
Oh, we have to have you at the mic, I'm afraid, because the people of the webcast can't hear you otherwise. Yeah, come on. Yeah. So here, just going to reiterate the question. So the question was, how did the salmon... So could you repeat the question? I'll repeat it again.
How did the salmon get up to Columbia past all those dams?
How did the salmon get up the Columbia past all those dams?
Well, they do it with some difficulty. There are 9 main stem dams on the Columbia. Each one of those have fishways, unlike Chief Joseph Dam, which is the one immediately up above the confluence of the Okanagan with the Columbia, which is a high dam and is impassable. So they come through those fishways, but there are years, and of course there are difficulties that one has to deal with, and I'll allude to Marcus's talk on climate change. In 2015, there was a thermal event in the Columbia River that put temperatures at record levels, and in spite of having more than 200,000 adult sockeye headed back to the Okanagan, there were essentially 12,000 that made it to the terminal spawning grounds. There was a 97% mortality due to this thermal event that pushed temperatures in the Columbia above the critical lethal for sockeye salmon and most salmon. So climate change poses a really complicating factor in the future. But for the present, they get through the fishways. You can return large numbers of fish to the spawning grounds, and the productive potential is still there intact in the Okanagan for this particular species.
Thanks, Kim. I think I saw another hand. Is there another one? No worries. There's time at the end for more questions. So moving on to our next speaker, Greg Utzig. Greg is a conservation ecologist and land use planning consultant. He's a member of the Columbia Basin Regional Advisory Committee, the Upper Columbia Basin Environmental Collaborative, and has participated in the International Collaborative Modeling Work Group. So it's great to have Greg here today. Thanks, Greg.
Thank you. I just want to make sure I know how to use this. Which one is the? Okay, great. And I can just use that. Okay, I was asked to speak on wildlife and fisheries issues broadly. I kind of changed it a bit to say environmental consequences and opportunities because I'd like to talk about both. But I'm mainly going to concentrate on what has been lost and what are the things in terms of environmental function, what are we trying to restore? What are our objectives? A lot of what I'm talking about is from a project that I was involved in, which was sponsored by the BC Fish and Wildlife Compensation Program. And it started back in 2005. And it was mainly because of the fact that we built these dams in British Columbia, but at the time we built them in the 1960s, there were some environmental impact studies done, but by today's standards, they would be considered completely inadequate. And oftentimes they amounted to counting the number of animals that might disappear. And there was no discussion of habitat loss or other effects on environmental ecosystem function. The objectives of these series of studies were to update our understanding, to assist in prioritization. We were spending around $4.5 million a year in a compensation program in the Columbia Basin, but yet we don't know what we're compensating for because there were never any studies done before the dams were constructed. And also, so therefore, to use this for strategic planning and reporting on the progress in terms of mitigating what the actual effects were. This is typical of the kind of assessments that were done back in the days of the typewriter. And you'll notice that basically they are just a listing of how many animals we thought might be displaced. The study actually looked at all of the BC Hydro-related dams in the Columbia Basin. I'm only going to concentrate on the treaty dams as well as the high Revelstoke because it's also a large one. The other ones that were originally looked at in the study are quite a bit smaller dams and not treaty dams. And also Kootenay Lake was considered in the study because it's impacted, because it's downstream of the Libby and the Duncan. The main approach was to try and find out what ecosystems were in the areas under the reservoir. Of course, there was no ecosystem mapping done prior, no aquatic inventory done prior to the dams. So we had to go back to 1950s air photos in most cases to get information, as well as a series of maps that were produced in the late 1940s and 1950s. Beautiful artwork, hand-drawn maps, actually. We looked not only at the mapping the ecosystems, but also we tried to estimate primary production that was going on, which of course becomes much more relevant now when we're talking about storing carbon, because that's what primary production is. We tried to assess the habitat losses, looking at aquatic losses, as well as wetlands and floodplains, which were quite significant, as well as terrestrial uplands that were flooded as well. And looked at it from a species impact, how many species and how severely were different species impacted, and lastly, a look at compensation options. It was a series of 13 studies. I was involved in a couple, but I just really want to note there was a lot of people involved in this project. My name ends up being on the summary, but I did a small portion of the work. This is typical of what we had to work with. Was out of the archives came these old 1950s air photos, as well as these hand-drawn maps, which actually are the only record of the streams that existed under the reservoirs originally. This was, for those of you from BC, this is before trim mapping. Trim mapping doesn't include the reservoirs. This is resulting output of GIS exercise showing the various ecosystems that were in existence. This is the Big Bend area just above the Mica Dam. And you can see tremendous wetlands and floodplain forests were originally there. And in terms of habitat for anadromous fish and other species, of course, you can see the complexity of the river systems that existed at that time. In terms of area flooded, the arrow ends up being the largest, but as you can see from the different colors in the graphs, I won't go into detail on that, there's quite a diversity in the reservoirs in terms of what kinds and amounts of habitats that were displaced by the reservoirs. In terms of looking at primary productivity, I'm not going into the details on how we assess this, but it was a combination. There was measurements done in the reservoirs. There has been some measurements done in some of the lakes, but a lot of it was extrapolation from other lakes and other river systems, and in the end, in some cases, expert opinion. Just to point out one thing that's quite important is you'll notice this is forested ecosystems, and of course, as they get older, these would be an old growth climax ecosystem. This would be a young cirrus after a disturbance. Is that in relation to the other kinds of ecosystems, forests end up playing a big role. This is the outcome of totaling it by reservoir. And you'll notice there's a scale change on this one here. Because the Kinbasket was dominated by large floodplain forests and upland forests, the amount of gross primary productivity occurring under that reservoir before the reservoir is huge. And this is a resulting productivity in the reservoir itself after the dams. So in terms of carbon capture and storage, we've reduced our opportunities dramatically. And the other ones, it's not quite so different. I think the other thing to emphasize, and this is just a different way of displaying the same information just in terms of percentages, is that each reservoir is unique in terms of trying to mitigate the ecosystem impacts. The amount of area taken up by these various types of ecosystems proportions are quite different. Arrow, there was the original upper and lower Arrow lakes, which were a substantial portion of the flooding. There were a number of lakes involved in Kinbasket, whereas the Revelstoke Reservoir, it's basically terrestrial ecosystems that have been displaced as well as the main river itself. In terms of looking at the losses, the way in which it was done for this study was to look at the proportion. There was a basin, a drainage basin established for each of the reservoirs, and then we looked at the proportion loss of the various types of ecosystems within that basin. This is looking at rivers and streams, and the proportion of loss is what's given in the upper part of the graph, and the red would be, of course, very high. In other words, we're looking at 95% loss of that particular stream class. Oops, sorry. These are the ones with the highest impacts. Of course, they're low gradient streams and low elevation, low gradient streams. And we're looking at extremely high percentages of losses. And from a salmon restoration point of view, this becomes very important because those are, of course, your prime salmon use areas. The other losses were also in other smaller streams, which for kokanee and other species are also, and trout are very important in terms of spawning grounds as well. Lakes, some people equate reservoirs with lakes. If you've ever spent a year on a reservoir, I think you'd agree that it's not the same as a lake. But we've gone from what was 4 large lakes to the Arrow Lakes as well as Kinbasket, 2 in the Kinbasket area, which have been lost. So we're down from 4 to 2 in the Columbia Basin, and we've got 3 new large reservoirs. Medium-sized lakes gone from 7 to 3, gained 1 medium-sized reservoir, and 4 smaller reservoirs, which were not part of the Columbia River Treaty. Fish species impacts. There's 47 species in the Columbia Basin. 27 are native, and then there's lots of introductions as well. and 9 species are endemic. We looked in detail at 24 species, and as we'll see in the next chart, it's quite complicated in terms of how each species, because they have different life histories, they occupy different parts of the basin, the way in which their impact is actually unique for each species, in some case unique depending on the reservoir. And the terms of reference was we were not allowed to look at salmon or consider salmon because it had nothing to do with BC Hydro. It's a Grand Coulee problem, so that's not considered in these fisheries impacts. This is just a summary. It's kind of similar to a graph that Kim had in terms of how the impacts from the changes from the dams has affected each of the species. And as you can see, sturgeon, it's a whole basically across the board, whereas some of the species, it's less critical. And then we can move on to looking at terrestrial and wetland habitat losses, and a similar type of analysis was done where we looked at the percentage loss for each reservoir, and then these are summarized regionally by climatic regimes. And when you look at the terrestrial habitats, wetlands, shallow waters, gravel bars, and cottonwood floodplain forests are the most impacted. And even when you look at the moist climatic regime and the dry climate regime, again, it's very high. The dry climate regime being the Libby, impacts of the Libby Reservoir. We also went on to look at individual species, and there are 289 resident vertebrate species in the dam units. An impact rating system was developed, and it was based on loss of each species. There's a database for the Columbia Basin which looks at the different habitat requirements of each species. For example, migrating waterfowl, you're only looking at shoreline habitat and shallow water habitats, versus deer, you're looking at winter range, you're looking at summer range, you're looking at migration corridors. Basically, the question was, how do these reservoirs affect the various life cycle needs of each of these different species? And then they were rated from 0 to 5, depending on how many parts of the life cycle were impacted, as well as how severe was the impact in terms of the percentage loss of habitat. And these were then summed up by the number of species and the degree of habitat for each of the reservoirs. So in terms of severity of habitat, the larger reservoirs tended to have the highest, Kinbasket in particular. Arrow Reservoir actually had the greatest number of species impact, partly because it's so long and it goes through from the drier interior cedar hemlock up to the quite wet cedar hemlock. So there's a wider range of species present. And of course, anything that depended on wetland and riparian habitat was, of course, severely affected. As I indicated, 70, 80, and sometimes 90% of that available habitat was destroyed by the reservoir flooding. Also picked out a number of species that had the highest ratings. We ended up with 3 amphibians, a reptile, 15 mammals, and 45 bird species that were considered a very high priority in terms of compensation, mitigation, and attempts at habitat restoration. There's also other things that are taken into account that is just in a broad sense that are sort of cumulative effects of these individual species effects, which would be things like loss of biodiversity in general and effects on the food chain. Loss of keystone species, of course, amplifies any particular loss. And then there's the whole question of ecological functions. And of course, we didn't consider salmon, which of course ends up being very important when you look at some of the data on the way in which salmon are taken out of the streams following spawning and provide fertilizer for adjacent floodplain forests, as well as a very important part of the food chain for grizzly bears, eagles, and whatnot. Uh-oh. I at it. Okay. Thanks. And lastly, what the report looked at was what are potential compensation options. And I'm not going to go through these in detail, but basically the compensation options that were looked at under this particular study were things that assumed that the dams would be operated as they have been since the treaty and are being operated now. What I would like to take my last couple minutes to talk about is some other options from another report I've been working on. As I said, this one basically looked at keeping the operating regimes as they are. I consider the possibility of the renegotiation of the treaty opens that up to say, what can we do under a restored treaty where we would operate these dams differently than what was agreed to 40 years ago? And so I've been involved in another study which was looking at, which is called the Mid-Arrow study that was referenced earlier, where we're looking at changing the operating regime for the Arrow Reservoir. As you recall from what I said previously, it's the one that's had some of the biggest impacts. It's also one that produces less electricity for British Columbia, so the potential cost benefit is much more positive for British Columbia, although clearly changing the operating regime will have impacts in flood management and hydro production downstream in the United States. This look up spaghetti. The dark blue is the average of Upper Arrow Lake prior to the construction of the dam, and this is the range from, I think it's from 1920 to 1968 of the level, seasonal levels for Upper Arrow Lake. The upper one, the dashed line, is the average operation of the Arrow Reservoir, and these are individual years from 1960 up to 2015, 2016. So you can see there's been a substantial change, and obviously the level has been changed dramatically. What is proposed in one of the scenarios, the favored scenario out of the Mid-Arrow study, is to change the way in which the dam is operated, to say that in 6 out of 7 years, the dam would target this sort of elevation with some opportunities for going 10% above and below that, which stabilizes the Arrow and has numerous potential benefits from ecological point of view. And 1 out of 7 years, to try and mitigate some of the flood impacts downstream, is to look at, in the years that's projected to be maximum flood, is to allow the Arrow to full pool in 1 out of 7 years. These numbers didn't just sort of come out of the air. What we did was we looked at the flooding in the natural Arrow system and said, how often were the forests around Arrow Lakes? Arrow Lakes actually had quite an extensive flooding history. And basically, areas that remained flooding were flooded less than once every 7 years, in which case it should do. But the other important question is the duration of the flooding. So the way in which this proposal is set up is that in this once in 7 years, you can go to full pool, but above 1430 feet elevation, you never allow it to be flooded more than 35 days, which is consistent with the flooding which occurred naturally in the forested areas surrounding Arrow Lake. So our hypothesis is if you can maintain this kind of regime, you can potentially reforest and recreate the ecosystems above 1430 and still provide some flood control downstream in those critical years once in 7. There's a few potential problems with this. I've worked with Jeremy from BC Hydro looking at how good are we at projecting which of those years are going to be that 1 in 7 year, and there are some issues around that. Our ability to predict that is problematic. I'm sure with climate change it's probably going to get worse. But there are options for looking at alternatives. Not only are there gains from an ecosystem point of view, but people dealing with recreation, of course, prefer this kind of option. And in terms of power production on the Clumber Power Corporation dam on the Arrow Lakes, actually this scenario produces the same amount of electricity as is produced today, because What happens now is that when Arrow Lake or Arrow Reservoir is drawn down, they actually shut the reservoir off because there's not enough head to run it. And this, under this scenario, it never goes that low. So you get less peak power, but the same amount of total power, more or less. And that's it. There's references, I think this is being made available. Those are references for the studies that I've summarized here. Thanks.
Thank you, Greg. Any quick clarifying questions for Greg before we move into general discussion? Okay. Can I have the panelists back? And just please come to a microphone. I think there's one there. I'll start off with a question for John while people get organized. John, are you ready for a question? Or give him a chance to sit down. Your microphone's on. Okay, so John, what can an organization like the CWRA do to ensure its members are equipped to respond to the kinds of challenges of ecological change in the Columbia and other basins that we've just learned about?
Well, the question comes down to professional alliance. As probably most people know, that under the current regulatory circumstances in BC, much of the overview of the way hydrology systems work and the compliance with the BC laws are done by professionals, normally quite often hired by companies. And I think that what we're seeing from the analysis done on the Columbia by Marcus and others is that the Columbia hydrology is going to change dramatically, and we have to move to more an adaptive way of managing resources rather than prescriptive. And I think that the CWRA needs to make sure that the requirements of professionals, geoscientists and engineers, are more oriented towards adaptive management than they have been in the past. And I think that one of the key results of this work is to make sure that professional people, scientists who are involved in advising clients and governments take on a more adaptive management model than they have done in the past.
Thanks, John. Got a question here.
Thank you. Yes, 4 interesting science-based presentations. And I guess my question is, how can all of this good science contribute to the treaty renegotiating process? Are we sitting here talking amongst ourselves as scientists, where there are a group of negotiators on the other side of the continent negotiating the treaty? What are the institutional mechanisms that are going to enable this good science to contribute to the renegotiating process?
I'm going to let you guys decide who wants to answer that.
I can start. Do you want to take that, John? Greg?
Well, I'll just say I can only speak for myself, but I'm making a point of trying to be involved in whatever opportunities arise. As the minister mentioned, there was a series of public input opportunities throughout the basin, and myself and a number of other people I'm working with took advantage of those. We have Kim and myself have participated in the ecosystem-based function workshop, which hopefully is feeding into some of the negotiating strategies. The mid-era report that I referenced actually was sponsored, and it was sponsored through the negotiation committee for British Columbia and was done jointly with funding from BC Hydro. There also was an international modeling team, which a number of people in the room here have been involved in, which hopefully is feeding some information into the negotiations. And I also am sitting with the Columbia Basin Regional Advisory Committee, which is another opportunity to provide input. In fact, it was only 10 days ago, a number of us in the room who are involved in that process met directly with the Canadian negotiator. He spent a day and a half at that meeting. So I think he's making an effort to try and involve people as much as he can.
Thanks, Greg. Other questions? Great. The microphone will come to you.
Yeah, this is a question about the politics, and maybe we don't have the right people in place, but I'm hoping, is this on? Yeah.
Yeah,
I'm
we can
hoping
hear you.
maybe John has significant political experience. And forgive me, perhaps, despite all the excellent ideas and proposals that you especially have been articulating today about ecosystem function, how we can include that in treaty, I remain skeptical, particularly in light of the BC decision. The regional recommendations from the U.S. side to their federal negotiators are far more robust in respect to including ecosystem function in a renegotiated treaty. But I have to say I remain skeptical of the will of the provincial government, and following that, the federal government in Canada, to really go beyond lip service to that particular function. I'm hoping maybe you can provide some really more concrete evidence. And I'll just, for those who are not entirely aware, I've been doing a little homework here. The BC decision has 14 principles. Number 7 and 8 address ecosystem function. Number 7 is the only one that really says anything very significant. And what it says basically that ecosystem values are currently, and I emphasize that word, currently, are currently and will continue to be an important consideration. So they don't really make a concrete statement that they plan to do anything more than they've been doing over the last decade or two. Whereas the United States recommendation very seriously says we're going to increase that aspect if we can. So I wonder if you can provide us with any hope from your close working with various people who are involved in political decision making over the will of the BC government or the Canadian government to really be serious about this aspect of it.
Well, just two comments on that, John. One is that there is a fairly comprehensive set of advisory groups in the Kootenays that have been, and Greg alluded to these, and I know Kathy Eichenberger personally as the chief negotiator for the BC government, and I genuinely believe that she's committed to listening and engaging with that range of communities in the Kootenays, and a lot of these people are pushing for not only maintaining the ecosystem function, but in many cases, improving it. But my particular beef is, as you saw, trying to place values on that so that it can actually enter into the cost benefit and the final resolution of the way that Columbia is negotiated. And my understanding is that the provincial government did undertake work with a large group of consultants a couple of years ago to look at the changing value of things like irrigated agriculture in the Columbia, on both sides, but mainly on the American side of the border, under different climate scenarios. And so one of the points I was trying to emphasize in my presentation is that the ecosystem values are not static. They're actually going to grow. And if you saw Marky's presentation, there's relatively more water in the Columbia, in the headwaters in Columbia going forward. And so that's going to have more value in providing ecosystem services downstream. And I think the BC government's alive to the fact that they have a real opportunity to negotiate higher returns back to Canada by putting some values on these ecosystem functions than they have in the past, flood control and power. And I'm hopeful that will take place. But to make that happen, we need a bit more science than we've got in order to buttress that analysis.
Thanks, John. Got another question?
If it comes to,
Greg?
this is a question for Kim Hyatt.
Okay. Greg's just going to quickly comment on the last question, and then we'll go to your question, sir.
I don't want to contradict John, but I share your concerns. And what I'm concerned about with the monetization is that if the U.S. is willing to pay, we'll forego our ecosystem function gains if they're willing to pay enough. And that's the real fear. I think it's really important that we emphasize that ecosystem function gains have to be made in ecosystems. Dollars isn't going to buy it back. Spending $4 or $5 million in mitigation, there's no more bottomland to buy back. There's no more rivers that are going to replace the Columbia. Those low elevation, low gradient streams don't exist somewhere else that we can buy them. We need to change the way we manage the reservoirs. The one really positive thing that I think comes out of John's presentation is this idea of experimentation and adaptive management. And I would add the important word in there is active adaptive management, that we experiment with operating these reservoirs in a different way and explore where we can find these ecosystem gains.
Thanks, Greg.
A question for Kim Hyatt. Given your experience with the Okanagan, if it came to pass that Canada and the US in their wisdom agreed to bring salmon back to the Upper Columbia, could you give us any idea of what we're looking at in time? Are we looking decades? What are we looking at to actually make it happen so we can all be realistic?
Well, it depends what level of restoration you're hoping for. I mean, if you're looking for simply reestablishing naturalized populations of salmon, anadromous salmon, anywhere above Chief Joseph and Grand Coulee, then a matter of 10 or 20 years would probably suffice to do adaptive management to demonstrate the viability of that. But if you're looking at essentially exhausting the potential for restoration of anadromous salmon throughout the Upper Columbia Basin, you're talking about generations of time. I mean, this would be a very long-term sustained effort. I mean, Chief Christian and First Nations are on record as saying these are multi-generational aspirations, and the vision covers that kind of time span, something that contemporary societies often unwilling to make a commitment to, but certainly First Nations already have made that kind of commitment.
Thanks, Kim. Well, this has been a great discussion. We're actually out of time, so I'm just going to wrap up with a few concluding comments. The Columbia River Basin ecosystems face major challenges due to past actions, as Greg and Kim have shown us, and especially due to future climate change. As Marcus's presentation showed, even the best case scenario shows significant warming. So we do have to plan for that, and it really highlights the significance of BC's position, especially with changing hydrology and potential southern water scarcity. I should note that in the climate change adaptation world, there's a very significant move towards ecosystem-based restoration and conservation in response to climate change impacts like flooding, heat, species risk, but also because of carbon sequestration, human health benefits, and other co-benefits. There's a lot more research needed on this, but these benefits are actually measurable economically and in other ways, as John has demonstrated. And so we do know what to do to some degree, and we do have some direction on how to move ahead, as both Kim and Greg outlined. And I think it's really important to end with a recognition of the importance of working together with First Nations, bringing Indigenous knowledge and all those thousands of years of understanding how the ecosystems thrived, together with Western science, as the Okanagan Project has demonstrated. So thank you very much for your contributions, and we look forward to continuing this discussion this afternoon. If you have questions that didn't get answered, please bring me your card from your seat, and we will look at those for the closing discussion hour. And then I believe Rolene has some very important information about where lunch is. Thank you.